Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving deep into the fascinating and frankly pretty complex world of multi-agent LLMs, specifically how they coordinate and reason collaboratively.
Exciting stuff. Multi-agent systems are, I think, the next big leap in AI. The ability to have multiple AIs working together, problem solving, that's where the real power unlocks.
I'm a little more cautious about that kind of enthusiasm. Collaboration is notoriously difficult, even for humans, and I'm not convinced we've cracked the code on how to make machines truly work together rather than just simulate it.
I'm with Sarah to an extent. It feels like we're building impressive tools, but are they actually understanding what they're doing when they collaborate? It's more pattern recognition than genuine coordination, isn't it?
That's a great point to kick things off. Let's say we're talking about a team of LLMs designed to, manage a complex supply chain. What does genuine collaboration look like in that context?
Well, ideally, each LLM would be responsible for a specific part of the chain. Maybe one handles logistics, another manages inventory, a third deals with suppliers. They'd need to communicate effectively, sharing information, anticipating problems, and adjusting their strategies in real time based on what the others are doing. That's how a human team would work, right? But faster and with access to way more data.
Right, but how do they communicate effectively? Is it just passing text back and forth? Because that's not really collaboration. That's just a glorified chat room. True collaboration involves shared goals, understanding each other's constraints, and even adapting your own behavior to help the team succeed. Do LLMs actually understand those concepts, or are they just generating statistically likely responses?
And understanding the world around the problem. A real supply chain exists in physical space and time. The LLMs need to be able to reason about delays, distances, weather impacts, all that spatiotemporal stuff I keep banging on about. Just crunching numbers isn't enough.
Okay, so we've established a high bar for what genuine collaboration should look like. Where are we currently falling short? What are the specific challenges researchers are grappling with?
I think one of the biggest challenges is context. Getting these LLMs to understand the full context of the situation, not just the immediate input they're receiving. That's where context engineering comes in, feeding them relevant information, structuring their knowledge base, so they can make more informed decisions.
But isn't that just more data, more context? At some point, you hit diminishing returns. You can't just throw information at a problem and expect it to magically solve itself. These models need to be able to reason about the context, not just memorize it. That's where symbolic reasoning comes in, the ability to represent knowledge in a structured way and apply logical rules.
But deep learning is learning these complex relationships, isn't it? The models are extracting patterns from the data that allow them to make inferences and predictions. It's not just memorization, it's generalization.
But what about novel situations? Scenarios they haven't seen in the training data. That's where the lack of true understanding becomes apparent. They can extrapolate, sure, but they can't truly adapt to fundamentally new challenges because they don't have a model of how the world works.
That resonates with some neuroscientific thinking I've been doing. If we look at how the brain handles collaboration, it's not just about individual neurons firing in response to stimuli. It's about the dynamic interplay between different brain regions, the constant adjustment of connections based on shared experiences. How can we build that kind of neuroplasticity into multi-agent LLMs?
That's fascinating. So you're suggesting we need to move beyond just feeding them data and start modeling the actual learning processes that occur in the brain?
Exactly. Imagine if each agent in a multi-agent system could dynamically adjust its internal representations based on the actions and feedback of the other agents. Like one agent sees another successfully navigate a particular problem, and its own internal model is updated to reflect that success. That's how humans learn from each other, right? Through observation and imitation.
That's interesting, but how do you represent those internal models? Are you talking about more layers in a neural network? Because I still think that's fundamentally limited. We need a way to represent abstract concepts, relationships, and goals in a way that's independent of the specific data they've been trained on. That's where neuro-symbolic approaches could be really powerful.
And how do you represent those concepts in a way that allows them to reason about space and time? A concept like delay is fundamentally temporal. A concept like distance is fundamentally spatial. You can't just represent those as abstract symbols, you need to ground them in a coordinate system, a framework for understanding how things relate to each other in the real world.
Okay, I see your points, but isn't it possible that deep learning will eventually figure out how to represent those concepts implicitly through sheer exposure to data? I mean, these models are already doing things we never thought possible just a few years ago.
It's possible, sure, but I think we need to explore alternative approaches in parallel. The brain is incredibly efficient, and it's not just a giant pattern recognition machine. It's constantly building models of the world, making predictions, and adjusting those models based on feedback. We need to find ways to incorporate those principles into our AI systems.
Exactly. And that involves understanding how the brain represents knowledge at different levels of abstraction. You have low-level sensory information, but you also have high-level concepts and beliefs. We need to bridge that gap to create systems that can seamlessly integrate data with symbolic reasoning.
And that integration needs to be spatiotemporally aware. The brain doesn't just represent information in isolation, it represents it in the context of where and when it occurred. That's crucial for understanding causality and making predictions about the future.
Let's dig into some real-world examples. Consider autonomous driving. Imagine a scenario with multiple self-driving cars navigating a busy intersection. They need to coordinate their movements to avoid collisions, optimize traffic flow, and respond to unexpected events like pedestrians or cyclists. How can we apply these concepts to that problem?
That sounds like a perfect application for multi-agent LLMs. Each car could have its own LLM, constantly monitoring the environment, predicting the behavior of other vehicles, and communicating its intentions to the other agents. The more data they have, the better they'll be at anticipating potential problems and coordinating their actions.
But what if the situation is completely novel? What if there's a sudden road closure or a malfunctioning traffic light? The LLMs might not have seen that specific scenario in their training data. That's where symbolic reasoning becomes essential. They need to be able to apply general rules about traffic laws and safety to the specific situation at hand.
And they need to be able to reason about the physical constraints of the environment. How long will it take to stop? How much space is available to maneuver? These are spatiotemporal calculations that require a deep understanding of physics and geometry. You can't just rely on pattern recognition. You need to be able to simulate the world and predict the consequences of your actions.
So in that scenario, how would a neuro-inspired approach differ from the current deep learning paradigm? How would we model the interactions between the different agents and the environment?
Well, I imagine we'd still use deep learning to process the raw sensory data, the images from the cameras, the readings from the sensors, but we'd also need to incorporate some kind of higher level reasoning module that can interpret that data in terms of abstract concepts like risk or opportunity.
Exactly. And that reasoning module would need to be based on symbolic representations and logical rules. It would need to be able to reason about the intentions of other drivers, the potential consequences of different actions, and the ethical implications of those actions.
And it would need to be able to do all of that in real time, while simultaneously tracking the position and velocity of all the other objects in the environment. That requires a very sophisticated spatiotemporal reasoning engine that can efficiently translate between different coordinate systems and predict the future state of the world.
Right. It almost sounds like we need to equip each agent with its own internal physics engine, a simulation of the world that it can use to test out different scenarios and predict the consequences of its actions. That's a far cry from just feeding data into a neural network.
But wouldn't that be incredibly computationally expensive? Running a full-blown physics simulation for every agent in the system. That sounds like it would require an enormous amount of processing power.
That's where efficient algorithms and clever approximations come in. You don't need to simulate every single detail of the world. You just need to focus on the relevant aspects. And you can use symbolic reasoning to prune the search space and eliminate irrelevant possibilities.
And you can leverage the inherent structure of the world to simplify the calculations. For example, you can use symmetries to reduce the number of variables you need to track, or you can use hierarchical representations to decompose complex problems into simpler subproblems.
Okay, let's shift gears slightly. What about multi-agent LLMs in a collaborative writing context? Imagine a team of A's working together to write a novel or a screenplay. What are the challenges there?
That's an interesting one. I guess the biggest challenge would be maintaining consistency and coherence across the entire document. You'd need to make sure that the different agents are all working towards the same overall goal and that their contributions fit together seamlessly.
And you'd need to ensure that the agents have a shared understanding of the characters, the plot, and the themes of the story. That requires a level of symbolic reasoning that goes far beyond just generating grammatically correct sentences.
And you'd need to be able to track the temporal evolution of the story. to make sure that the events unfold in a logical and consistent manner. That requires a spatiotemporal reasoning engine that can keep track of the relationships between different events and characters over time.
So, how would a neuro-inspired approach address these challenges? How would we model the creative process and the interactions between the different agents?
Well, I imagine we'd start by training the agents on a large corpus of existing novels and screenplays. That would give them a sense of the different genres, styles, and structures that are possible.
But we'd also need to equip them with a set of symbolic rules about storytelling. Rules about character development, plot construction, and thematic coherence. These rules would help them to generate stories that are both creative and meaningful.
And we'd need to give them a way to track the temporal relationships between different events in the story. A timeline, a causal network, something that allows them to reason about the consequences of their actions and the overall arc of the narrative.
It's interesting, isn't it? How even in a seemingly abstract domain like creative writing, the need for spatiotemporal reasoning still emerges. It's almost as if the brain is fundamentally wired to understand the world in terms of space and time, and that any truly intelligent system needs to have a similar capacity.
Well, I think it's clear that multi-agent LLMs have the potential to revolutionize a wide range of industries, from transportation to entertainment. But we still have a long way to go before we can create systems that truly collaborate and reason in a way that's comparable to humans.
I agree, and I think that the current focus on deep learning is ultimately limited. We need to explore alternative approaches, like neuro-symbolic reasoning, if we want to achieve true AGI.
And we need to recognize the importance of spatiotemporal reasoning. Without a fundamental understanding of space and time, our AI systems will always be limited to pattern recognition and extrapolation. They'll never be able to truly understand the world or reason about its complexities.
So, looking ahead, what are some specific research directions we should be pursuing? What are the most promising avenues for future exploration?
I think we need to continue to scale up our deep learning models and train them on even larger data sets. The more data they have, the better they'll be at learning the complex relationships that underlie intelligence.
I think we need to focus on developing more sophisticated neuro-symbolic algorithms that can seamlessly integrate data with symbolic reasoning. We need to find ways to represent knowledge in a structured way and apply logical rules to solve complex problems.
I think we need to develop a new generation of AI algorithms that are fundamentally spatiotemporally aware. Algorithms that can reason about the relationships between different events and objects over time and space. Algorithms that can simulate the world and predict the consequences of their actions.
From my perspective, I think we need to draw more inspiration from neuroscience. We need to study how the brain handles collaboration, how it represents knowledge, and how it reasons about the world. We need to find ways to incorporate those principles into our AI systems.
That's a great point. I think that a multidisciplinary approach, combining insights from computer science, neuroscience, and cognitive science, is the key to unlocking the full potential of multi-agent LLMs.
I agree. And I think that we need to be willing to challenge our assumptions and explore new ideas. The path to AGI is not going to be easy, but I believe that by working together, we can achieve it.
Absolutely. And we need to be mindful of the ethical implications of our work. As we create more powerful AI systems, we need to ensure that they are used for good and that they benefit all of humanity.
Well, this has been a fascinating discussion. It's clear that multi-agent LLMs are a complex and rapidly evolving field, and that there are still many challenges to overcome. But I'm optimistic about the future, and I believe that by continuing to push the boundaries of research, we can create AI systems that truly collaborate and reason in a way that's comparable to humans. That's all the time we have for today. Thanks for tuning in to Cognitive Spirals. Join us next time as we delve into another exciting area of AI research.
Thanks, everyone. It was a great conversation.
Indeed. Until next time.
Goodbye.